Okay.
Before this class starts, you ever feel that pens are more print eligible when you write than pencils?
Legible?
Yeah.
Sure, I agree. They're darker than pencils most of the time. Yeah?
I mean, all your handwriting is all messed up in your pencil, but when you're writing in like a pen, it's more like a little bit more eligible and more neat. Or say.
Yeah, I don't know what we're talking about anymore. All I can say is that if you're going to write in pen and do math, then I don't recommend that because I have yet to meet people who. Yeah. Okay. All right. Today, chain rule. Now this is not like I've saved the hardest. We're going to do the hardest rule now. It's just the most important rule. All right. So I don't want you to come into this thinking like, okay, this is like the real hard stuff. All right. And when you look back on the rules that we've looked at, what are they? The power rule is the first one, product rule, quotient rule, right? And then we have chain rule. And then there's also the other ones that we just have to know, like the derivative of sine is cosine, things like that, right? Once we have this rule, like theoretically, we can take the derivative of just about anything. Now, we still have not looked at logarithmic functions and exponential functions. We will address those later, and we will talk about the derivatives of those. So I can't say we can do everything yet, but this is the last major rule, all right? So let's go ahead and talk about the rule first, and then we'll start doing examples. Here's what the rule says. It says if y is some function with some other function plugged into it. So things that would look like this, I'm going to give you some examples over here, something like this. Y equals sine of x squared plus 1. That would be an example of a function with a function inside. And in college algebra, we call this composition. Fog f of g of x, Goff g of f of x. Remember seeing things like that? Okay, that's what this is. And what we need to be able to do in this class is identify what the inner function is and what the outer function is. So what would be the inner function here? X squared plus 1, and the outer function would be the sine function. Okay, that's what we need to be able to do. So that's good that you recognize that. Now, the chain rule says if you want to know the derivative of this composition, it is not what you would hope it is, right? You might hope that it would be this. Something like that. Just real quick, you take the derivative of each one and that's it. But that's not what happens. With the chain rule, this is what you do. You take the derivative of the outer function first. I don't need that to be that big, sorry. Okay? Which in this case would be the derivative of which function? The derivative of the sine function. And then inside of that, you plug in that inner function, the inside function, right? This is the inner one, but no derivative on that one. I'm just going to put no DER, no derivative. You take the derivative of the outer function and you plug into it the inner function without a derivative, or without taking derivative of this. Then you multiply, and this is where the whole idea of the chain comes from. The chain being one link followed by the next link by the next link. So these links are connected through multiplication. The next link in the chain is the derivative of the inside function. And that's it. That's the chain rule. Okay? You need to see it in action in order to get it, but that's the rule as it's written. So this is the inner, but with the derivative, right? With the derivative taken. Now, do you remember that there's two types of notation for derivatives because Newton and Leibniz came up with the calculus and they had two different notations? Yeah. Okay, so let me show you the way Leibniz approached it. Leibniz approached it this way. I guess we'll leave this up here. Leibniz says if y is some function of u, and u is some other function of x. Now, I need to explain what this notation means, all right? Then dy dx. So let me go back to this. Let's say we have a function, right? G of x. And we're going to call it u. If we take this u and plug it in right here, isn't this the same as f of g of x? Isn't this still saying the same thing as that? Yes? Because g of x is u, and if I replace that u with g of x, I'm back to that. So this is the way Leibniz looked at it. And then what he said is, well, what is this, right? What is this? And here, what are the two variables in this problem here, in this equation? Y and u, right? What are the two variables here? U and x. So Leibniz said, look, I can take the derivative of y with respect to u in this problem, in this equation. I can do that, because y depends on u, so I can take this derivative. Remember, this is his notation. If this was y and this was x, he would write dy dx. Leibniz here would write dy du. And here, he would write what? Du dx, right? And so what Leibniz noticed is that if he's trying to find this, right? What's the derivative of y with respect to x? That if you take these two and just multiply them together, do you see that this should equal this? Because these du's would really kind of cancel, wouldn't they? These would go away and you get dy dx. So in some way, dy dx is just these two multiplied, this and this. So what I'm going to do today is I'm going to show you a couple of problems, and I'm going to use this method right here. I'm going to stick with this for a while. Then I'm going to switch over and I'm going to do some Leibniz notation. And then I'm going to try and do the ultimate method, which is the third method, the one that you really want to learn, which is the shortcut. And it's not a shortcut that, it's not like the power rule was a shortcut. Remember when I gave you the power rule, like the 3 comes down and then it's not like that. This is a shortcut where you have to be ready for it. Like you have to understand what's going on before we can just do it. Are you ready for some examples? Okay.
The left side is Newton's and then the right side is...
This is Leibniz. This is Newton's. Or yeah, you could say this is the standard chain rule if you see it in most books. This is the chain rule with Leibniz notation. All right. I'm going to keep that right there. No, I'm not. I'll just put it up here. Remember, if y is equal to some function of x, right, composition, then y prime is going to be equal to f prime with g plugged in, and then times the chain g prime x. And let's start with this example, this sine of x squared plus 1. I've already told you before, I hate to put on the board mistakes. But I think it's important to see what students do incorrectly so that you can avoid it, all right? And this is the wrong thing, and this is what students do. Some students will do. They will say the derivative of this is cosine of 2x. So what did they just do? They took the derivative of sine and said, derivative of sine is cosine. They say, hey, derivative what's in here is this. And that's it. This is incorrect. It's kind of close, though. It's actually pretty close, but it's not correct. What you have to do is apply the chain rule. So I'm going to write down, just to get us started, I'm going to write down what is f of x and what is g of x. So tell me what f of x is in this problem, and tell me what g of x is in this problem. You already told me. Sine, right? But how am I going to write that? I can't just write sine, because it would just be sine. We say sine x, right? Sine x. And then g of x is x squared plus 1. So if you took x squared plus 1, right, and you replace this x with it, then this would become sine of x squared plus 1, which would be that. Is everyone comfortable with that? Okay. So that's what f is, that's what g is. In the chain rule, I do need to use the derivative of f, right? And I need to use the derivative of g. So let me take the derivative of each of these. F prime of x would be cosine x, right? And g prime of x would be 2x, right? Agreed? And that's it. We're ready. We can come back over here and write the answer down. The derivative of that y up there should be the derivative of f, but with what plugged in? The inner, right? The inner, no derivative. So what I want to do is I want to come over to the f prime, and inside of it I don't want to plug x, I want to plug in what? G of x, which is x squared plus 1. So I'm going to replace this x with x squared plus 1. So it should be cosine of x squared plus 1. With me? That's the derivative of the outside function, sine, with the inside function plugged into it. Then chain rule says times the derivative of g. Just the derivative, that's it. What is it? 2x. And then what I'll do is I'll rewrite it as 2x cosine x squared plus 1. And that's it. Okay? It can get more complicated, but this is the, this is the essential part here. If you understand this, then it's just a matter of putting things together later. All right, let's do a different problem, all right? So let's do, how about this? How about secant of the square root of x? Okay, what do you see here? Do you see product rule?
Yeah. Times x to the 1.
Okay, is that secant times root x?
No, it's
Secant of root x, right? You can't, this is never going to be multiplication with a trig function, unless that said this, like secant x times root x or something like that. But the secant, just by itself, it's implied that this is the argument of the secant function. So this is sitting inside of there. Okay, so that is not product. It's not quotient, right? We don't have a quotient. There's no division. So do you see that it's a chain? Do you see its composition? You have an inner and an outer function. In this case, what's the, doesn't matter which one you want that you start with. Secant's the outer. That's your f then, right? So your f of x here is secant x, right? The outer function, the inner function, which we'll call g, is what? Square root of x. And as long as you can take the derivatives of each of these, you should be in business. So what's the derivative of secant x? Good. Secant x, tangent x. You have that memorized?
No, I have to.
See, very good. You have your sheet sitting there on the desk with you. That's the right way to be there. And then the derivative of root x, 1 over 2 root x. I told you it would come up a lot, right? All right, so once you know the derivatives of each of the pieces, right, each of the functions separately, now you can just go back and apply the chain rule. So the derivative of this should be the f function, right? The derivative of the f function, which is this one, with what plugged into it? Root x. So I'm going to replace that x with root x, replace that x with root x. It's going to look weird, but this is what it is. Secant root x, tangent root x. That makes sense? Times the derivative of g, 1 over 2 root x.
Just to clarify from the secant and
Yep.
tans roots, you're just multiplying it with, it's just like,
I'm not multiplying, I'm composing the functions. I'm plugging this function g into the derivative, right? This is what this means. G is going inside of the f prime. So this g, this root, is going inside of this function. So it's going here and here.
okay, just clarifying, thank you, sir.
Yep. Mm-hmm.
So would that just be like 1/2 x to
Yeah, so is there anything we can do with the root? I mean, can I cancel? Remember, in trig functions, these arguments are trapped. You cannot cancel things out, right? Like I can't do this. This is the classic example. If I have sine x over x, and I cancel that, what is that? It's a sin, right? That's kind of cheesy, it's stupid, right? But that is a sin to cancel your x's like that. You cannot do that. This x is trapped inside there, and you cannot do that. All right? So the same thing here. I cannot like cancel one of these. So, how do you mean?
It's like secant square root x, tan square root x over 2.
Yes. I'm going to do that. I'm going to just rewrite it maybe as a fraction. And this, at this point, it's really not any more correct, you know? That's what I would do. If I were doing that problem, that's the way I would write the answer. I would just write that.
Would like one half x to the 1/2, and then
All on one line? You could do it that way, yes. X to the negative 1/2.
Oh,
Are you going to leave it up top? Yeah.
Okay.
Yes.
Again, I'm super sorry. I know you went over this.
No, it's okay.
But with the 1 over 2 root x,
Yes.
how do you get to that?
Well, we worked through it. What we did is we turned this into x to the 1/2. Then we used power rule. 1/2 came out, x to the negative 1/2 once we did power rule. Then that dropped down to the bottom. So this turned into 1 over 2 x to the half. And then x to the half is the root of x. And then what I said is, look, we're going to take derivative of this so many times that just you need to memorize this. If not, you can do the whole thing and get to it. But
I was just wondering how you got
yeah.
it. Thank you.
Good? Okay. All right. So far, we all right? Okay, let's try something slightly different. I'm going to almost do the same problem. Root secant x. Not secant of root x, root secant x. And
Is the outside function that, and then the inside?
yeah, so you don't see product rule, you don't see quotient rule, right? You see chain rule, you see outer and inner. Okay, what's the outer? Square root of x, right? Root x. The inner one is secant x. See, it's almost like they switched positions in this one, right? I did it so it's opposite of the previous problem. And our derivative is going to be different, like our actual derivative. Do y'all see that this is this?
Why is that again? Or I'm just not like seeing it.
Like the outside and inside? Okay, so the way I would encourage you to think of the outside and inside function is, let's say I asked you to actually plug in a value for x right now. Like take a number like 2. Plug it in there. What's going to happen to it first?
It's going to get rooted.
If I put 2 here, are you going to do secant of it first, or are you going to do root of 2? Secant first. So the secant function is the inner function. And then the next thing, after you would do secant of 2, you would then do square root. So the square root is the last thing happening. It's the outer function.
Like the order operation.
It's almost like an order of operations.
Okay.
That make sense?
Yeah.
Okay, so there's your outer, there's your inner. And now just derivative of each of them. F prime x, derivative of root x is 1 over 2 root x. Derivative of secant x, tangent x. We will have a quiz next class, just so you know. It's going to be a longer quiz than normal. It's going to cover power rule, product rule, quotient rule, chain rule. It's probably going to be about a 20-minute test, or a 20-minute quiz, just to make sure we're on the same page, because I need to make sure as we proceed that you've got all these rules kind of down.
So 4 problems, right?
You expect a minimum of 4. Yeah. All right, so the derivative of this should be the f prime, right, but with g plugged in. So this, replace x with secant x tangent x.
No.
Sorry. Thank you. At least you're paying attention. Secant x, right? G. Putting g into the derivative of f. Then just times secant x tangent x. Now this one's a little more interesting than the last one, because you can actually do something with those secants. Let me rewrite it so it might look a little different for you. This is secant x times tangent x over 2 secant x to the half, right? That's what the square root means. And this secant x on top is like raised to the 1. It's the whole thing to the 1 power, and then the whole secant x to the half power. It's the same base, isn't it? Different exponents? Positive 1/2, because you're doing 1 take away a half. 1 take away a half, and that would be 1/2, wouldn't it? So this should turn out to be secant x to the 1/2 times tangent x all over 2. Do you all see that? And what is secant x to the half? That's really just square root. So, and this 2 down here, I can write it like this. That's most likely what the back of the book would have. When you go and do your homework, I've said this about the product rule and the quotient rule, you want to try and make your answers look like the back of the book on every single problem. You do the derivative and then try and look at the back of the book and try and get your answer to turn into theirs. Now, if it's an even problem, you may not be able to do that, right? Because the back of the book doesn't have the answers to the evens. But I believe there's a solution manual in the library. If not, I'm sure there's one online somewhere.
There's one on Chegg.
There's one where?
On Chegg.
Chegg?
Yeah.
Is that the online books that you get?
Yeah, it's like $15 a month or whatever.
Okay. Well, so that okay? Y'all see the difference between changing what was the inner and what was the outer? Okay. Now I'm curious, what would you do with something like this? I'm going to keep that up there. But what if we started a problem and we had f, and inside g we had h of x? This is a triple composition. This is a function inside of a function inside of a function, which was totally allowed in college algebra. You could have, 3 levels to this thing, right? What do you think the derivative would be? Let's just go with gut instinct here.
Like the,
What do you think the derivative would be?
oh, like the over.
Yeah, like that.
Do you ignore the third composition, or do you just add it to the chain?
I don't know. That's why I'm asking you. What do you think? Do you think you're going to add it to the chain? So you think we're still going to do f prime, right? And inside of that, you think we're going to have something, but we're not going to take a derivative, right? What is the thing that you think is going to go in there? G of h of x. That is correct. Okay. Times now. What do you think?
The first one, so it would be times just GH of x?
G prime.
G prime would come next. G prime, and inside of that, h of x, and then times h prime of x. So look, this part right here, g prime h of x times h prime of x, this right here is like if the f wasn't there, right? And then that's the same rule. The only addition to the only added part to this is that if we have another layer to the composition, then we have to include the derivative of that layer with all the crap that was plugged into it plugged in. Let's do an example. Let's try, I want to keep that up there. I'll keep that up there also. Let's try this one. Y equals, how about, we'll go back to something nice. Root sine of x squared plus 1. I'm just trying to keep these kind of similar to things we've already looked at today. All right, how many layers to this function? 3 layers. What's the inside? Inside function? X squared plus 1. The middle layer, right, would be sine, and then the outer layer would be the root. So 3 functions, right? I could write them down. F of x would be the root x. G of x, which is the middle one, would be sine x. And then h of x, which is the inside one, would be x squared plus 1. And so if I put this in here and then all of that in here, I'm back to this. In this formula, I do need the derivative of f. I need the derivative of g and h. So let's find all their derivatives, just like we did before. 1 over 2 root x, g prime, cosine x, h prime, 2x. It's okay? All right, let's see if we can make any sense out of this. If I want the derivative of this, I'm going to put it underneath this so you can see it. I need the derivative of f, but with g of h plugged in. So what is the derivative of f? What's the derivative of f? 1 over 2 roots of x. But am I actually plugging x into that? No, you're plugging g of h, which is g of h are these two put together with this plugged in here. So you said it, sine of x squared plus 1. Do y'all see that's g of h of x right here? That's the h function plugged into the g function. Times. Now I need the derivative of g, which is cosine of x. So cosine of, but not x, what? H of x, which is x squared plus 1. Times, now finally, h prime, which is 2x. You can see how this can kind of get messy, right? Especially if I have like 4 functions or 5 functions. But there's a method to it. Do you see that there's kind of a pattern to this? That's why the third method that I'm going to show you today, the shortcut way, is the way that you want to start thinking. But first we need to have more of a structured, systematic approach. And this is it.
Well, I guess it wouldn't be too hard to combine all that.
Yeah, we could, okay, so what could we do here? We could cancel the 2's. We could put this on top of the other one. We can't do anything as far as putting, well, yeah, I wouldn't. You could try and go somehow turn it to some sort of cotangent, but I'm not going to mess with it. X would come out front, so not much. Yes?
So that would be the same as cosine x squared plus 1 over the square root of sine x squared plus 1.
Yes. Did you say this X or no? I don't know if you had said that.
Cosine,
X cosine of x squared plus 1 over root of sine of x squared plus 1. Yep, because it's multiplication, fractions, just, okay. What's the derivative of this? So you're thinking quotient rule because you see a quotient, right? I think most people do that because they see the quotient. Which I agree, we could do that. However, just tell me if you agree with this or not. Is this the same as 1 over x cubed plus x plus 1 to the 1/3 power? Is that the same thing?
Yeah.
Okay. And if I wanted to, could I take that whole thing and move it up?
Yep.
Yes, I could rewrite this as x cubed plus x plus 1 to the negative 1/3 power, right? And now if you look at it this way, do you see an inner and an outer function? Do you see composition? What would the inner function be? X cubed plus x plus 1. What would the outer function be? Something to the negative 1/3, right? Do y'all see that? I can do this without quotient rule by converting it to a chain rule problem. So what is the f I'm going to, what is the outer you said? F is the, you tell me, f and g. X to the negative 1/3, good. And g is the inside, x cubed plus x plus 1. And as long as you can take derivative of those, you're good. You're in business. The derivative of this should be, let's see, what's the derivative of that? Negative 1/3 comes out, x to the negative 4/3. That's just power rule. And then the derivative of g is really nice, right? 3x squared plus 1. And the chain rule says it's going to be the derivative of f with g plugged in without a derivative times the derivative of g. So you think we can write it down? The derivative? I'll put it right here. The derivative of this is f prime with g plugged in. So negative 1/3, but instead of x, I'm plugging in g, right? So x cubed plus x plus 1 raised to the negative 4/3 times g prime, which is 3x squared plus 1. And is that correct like that? It's not correct like that. There's something missing. Parentheses. Why? Yeah, I mean, students always seem to forget this parentheses, but is there a difference between this and that? Right? This is saying multiply the 4 times the 5, then add 1. This is saying multiply 4 times these together first, right? This is like, this whole thing over here is like the 4 times 5 plus 1. You want all this together, right? You have to put it in parentheses. I will take off on the test if you forget those parentheses. It won't be like minus 10 out of 10, but you won't get full credit. And that right there, I mean, you could drop this back down, right? And you could convert that to a positive 4/3, and then you could even go and convert that back to a root. But this right here today is the most important thing. Can we get the derivative? There it is. So we avoided the quotient rule completely there, didn't we? It actually turns out, believe it or not, you can throw quotient rule out completely by always turning things into a chain rule. I'll give you an example. I'm not going to work through it, but like if you had x squared plus 1 over x cubed plus x, right? That from last class. We would do derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared, right? But if I wanted to do it using chain rule, what I could do is write this as x squared plus 1 times x cubed plus x to the negative 1. So you see I brought the bottom up, but I'd still have to do product rule. I wouldn't be able to get away from that, but I wouldn't have to do quotient rule. Let's see, I went this far. Let's see if you could do this. This is going to be a good one. Let's call this y. Now I would probably say, if I were doing this myself, I would just do the quotient rule. Okay, that's what I would do. But I'm just showing you, you could turn it into this. So let's do the derivative here. Does everyone agree we have a product? Right there. Yes? So the product rule is the derivative of the first one times the second, plus the derivative of the second one times the first. So what's the derivative of the first one? 2x, that's straightforward, times the first one. Times the second one. Plus, now the derivative of the second one. Now you have to go do a chain rule. So you got to go set that up as its own problem and find its derivative, right? Figure out what f is, what's g. Understand? What's the inner function here? X cubed plus 1. Outer function? X to the negative 1. So you go do all that stuff, right? Get your answer, and then you'd stick that right here.
Did you say it was x cubed plus 1 or x cubed?
What's that?
Is it x cubed plus 1 or x cubed plus 1?
Did I say x cubed plus 1?
Yeah.
I meant x
You're
cubed plus.
looking backwards.
No. The inner function is x cubed plus x. The outer function is x to the negative 1. Sorry, if I said that, I didn't mean to. So the derivative of that will be negative x cubed plus x to the negative 2 times 3x squared plus 1. That's the derivative of this, okay, if you were to work it out. And then times the first function, x squared plus 1. Okay, so that's it. I'm just showing you we could do it without quotient rule. But I am leaving this part as like, okay, you would have to go do that on your own, right? On the side. All right, what do y'all think? Chain rule? Yeah?
Well, for the more complicated ones, but not for that one.
Yeah, I wouldn't use chain rule on this one. I would just stick to a quotient rule. All right, let's do something else. How about we look at Leibniz notation? I just want you to see it. We did this problem earlier, right? Was it sine? No, it was secant, right? Secant root x. Secant, right? It was secant. We did that earlier. Secant root x. Here's how Leibniz would have written this down. Leibniz would have still said I have an inner function and outer function, but he would have said, I'm going to write y is equal to secant of u, all right? Where u is the inside function. Then he would write below that, u is root x. And then he would take the derivative of each of these. So I kind of didn't give myself enough room here because I'm going to go off camera. So I'm just going to slide these to the left real quick. He wrote down y was secant u, and u was root x. And then he would take the derivative of y with respect to u, and that would be secant u tangent u. And here he would take the derivative of u with respect to x, which would be 1 over 2 root x. Do you see how that works? And then he would realize that his answer, y prime, which is the same as dy dx, is equal to dy du times du dx. It's these two multiplied together. Remember, because I said the du's would cancel? Du, and that's dy dx. So for Leibniz, he would write down secant u tangent u times what? 1 over 2 root x. And that's almost the same answer we had, except that his answer has u's and x's, right? Let's try and get it all to x's. So you'd replace the u's with what? What is u? Root x. So you just rewrite this. Secant root x tangent root x times 1 over 2 root x. And if you look back in your notes, we just got that same exact answer. Some people like Leibniz notation. Some people like the other one. It's really up to you. I'm not here to push one way over the other. Would y'all like to see another one with Leibniz, or no?
His sucks, man.
His sucks already? You don't have any? You don't like it? How about let me do one more. I'll try and sell you on it. What was the harder one that we did f of g of h? It was y was, what was it, root sine x squared plus 1. So let's see how Leibniz would have written this down. He would have said, all right, my outer function is root, right? So Leibniz would have said, I've got y is equal to root of something, right? And the something is this, right? Sine of x squared plus 1. So he would have said my u, the inside piece there, is sine, right, of something. And he would have called that something some other letter. Maybe he would use m. I don't know. It doesn't matter. And then he would say that the m is what? x squared plus 1. And he would actually, once he can get to something nice, he would say, okay, m is that. And then this almost in Leibniz almost starts to look like a table. Okay? You can go, this one right here, he could take d what, d what? dy du, right? And that would be derivative of root of u is 1 over 2 root u. And then here he could do du dm, which would be cosine m. And then here he would write dm dx, and this would be 2x. And if you multiply this times this times this, that should be the answer. Now, why is it the answer? What's dy du times du dm times dm dx? The dm's would cancel, du's would cancel, and that would be dy dx. That's the logic behind why it works. So now you have, what, 1 over 2 root u times cosine m times 2x. But now he would have to get everything back to x's. So let's start with this m. What is m? X squared plus 1, right? And while we're doing that, what's this u? What is the u? The u is sine of m, right? Sim. Sine of m. Let me do the u first. Cosine m times 2x, right? So he just says, all right, let me replace u with sine of m. And now he's got m's there. He'd replace both those m's with x squared plus 1's, and you would be at the same answer that we got. Okay? What do y'all think of this?
Makes a lot more sense.
You like this way? You don't have to think of the composition as much. You don't have to think of like f of g of h. It's all just make a table and plug in. So you pick your poison here, all right? It's up to you.
Are you going to know portion this later?
If you go pull a calculus student out of a classroom right now and you ask them to take the derivative of this, they better not write anything down. As far as like f, like writing down what the outer and inner is, and they better not make a Leibniz table out of it. They better be able to do it in their head, which is why the third method is the one I want to show you. All right? This is the short way, all right? But it's not like, I'm just trying to get you to where we need to be. I've taught this class many times, and sometimes I've started with the short way, and everyone like usually catches on to it pretty quick. But then when they go to do their homework, they can't do it. So I am showing these two methods first because I want you to have something to go off of if you're stuck. But ultimately, you want to be able to do it the way I'm about to show it to you. All right? You ready? Let's do it. So I'll do the same examples we've been doing. I'm going to erase this now because we don't need it. And this is going to seem childish and stupid, kind of. Let me do this one first. Sine root, secant. Secant. Was that the first one I put up there? Secant root x? Is that the first one we did? No. Sine of
X squared plus
Let's do that one first. Sine of x squared plus 1. Okay, that was the first problem I did. All right, you ready? Now here's where it gets kind of childish. You still need to figure out if this is composition, if you have a function inside of a function, which we do, right? And you're going to work with this like an onion, from the outer layer of the onion and work your way to the inner layer of the onion. In this particular case, there's only 2 layers, right? But this same process would follow if you had 10 layers to the onion. So I start with the outer layer, and I identify it. What is the outer layer of this thing? Sine of x. Or sine, right? The sine function. So now I'm going to use this eraser, okay? And I'm just going to stick it right here. And I'd like to ask you what the derivative of sine of an eraser is. Cosine of an eraser. Agreed? Okay, so just write that down. Cosine of the eraser. But what is the eraser? X squared plus 1. Okay, you have now done the outside layer, right? You have taken care of the outside layer. Now work your way to the next layer in. What's the next layer in? What's the next layer? X squared plus 1. What's the derivative of that? 2x. So you say multiplication, because you always do multiplication with chain rule, 2x, and you're done.
I like that one a lot more.
Yeah, me too. All right, next example. Y equals secant root x. All right. So for this one, I'll use my phone. You can use anything you want. That's the beauty of this. You can use your finger, it doesn't matter. So I have an outer layer and an inner layer. The outer layer here is secant, right? So I'm going to put my phone right there, and I'm going to ask you, what is the derivative of secant of my phone? Secant of my phone, tangent of my phone, right? Secant of my phone, tangent of my phone. Do y'all follow what I'm doing here? Okay, I told you it's kind of childish, right? Secant of my phone, but what's my phone? It was the root x, right? Tangent of my phone, but what was my phone? Root x. Okay, we've done the outside layer, right? The outer layer is done. Now you move into the next layer in, it's root x. Well, what's the derivative of root x? 1 over 2 root x. Multiplication, 1 over 2 root x. And that's the same thing we had, right? If you pick up on this and you're like, yeah, why didn't you show me this first? It's because I guarantee there are some students that won't pick this up as quickly. So I've got to show both ways. Didn't we do root of secant x next? Root of secant x? So let's look at that one. Y is root secant x. So for this one, I'm going to use this green towel. This green towel, make it just about that perfect size there. There we go. So what's the outer function there? The outer function is the root, right? So I'm going to say derivative of this is going to be equal to the derivative of the square root of that green towel. 1 over 2 roots of the green towel, which is secant x. I'm done with the outer layer. The outer layer is the root, right? I'm crossing out the root. Go inside, what's the next layer? Secant x, and I tack that on here. What's the derivative of secant x? Secant x tangent x. And if you look back in your notes, that's what we had. Right? That's what we had. So you want to do the 3 one now? Okay, what was the 3 one? It was root sine of x squared plus 1. All right, y'all ready for this one? We have an outer layer, which is the root, a middle layer, which is the sine, and then a layer inside of that, which is x squared plus 1. Do I have any questions? You sure? All right, I guess I'll use, well, you know what, on this one, I'm going to use, this is my arm. How about that, okay? So I have y prime, I'm going to take the derivative of the square root of my arm. What's the derivative of the square root of my arm? 1 over 2 roots of my arm, but my arm was actually sine of x squared plus 1, right? Times, now, we have peeled the first layer off. The first layer was the root, right? So we go into the next layer. What's the next layer? Sine of this mouse, right? Sine of the mouse. Derivative of sine of the mouse is cosine of the mouse. The mouse was x squared plus 1. I have now done, the middle layer is gone, sine. So I move to the next layer, which is x squared plus 1. What's the derivative of x squared plus 1? 2x. Does that match what we had earlier? Yes. Yeah, it's a little faster.
And then that would be cosine of x squared plus 1 times 2x. Well, no, you would get rid of the 2's. Okay.
This is the same one you asked me about, right? Just that x would be out there?
I think I caught it this time.
All right, so this seems pretty nice. I do too.
So we can use this method on our homework.
Oh yeah. Oh yeah. All the way through. Yep. All right, so how about this? How about cosine of x squared plus 1 over x cubed plus 4? What do you see? See a quotient rule. I see it also. And a chain rule. Composition. So which one are you going to do first? Quotient, you think? Isn't that quotient on the inside of cosine, though?
So it's the inner.
Isn't that, yeah, that quotient, the entire quotient, isn't that like one of the inside pieces to the onion? The outer layer of this onion is what? Cosine. So I'm going to treat this just the way I've been doing it. I'm going to get my towel out, and I'm going to do the derivative of cosine of the towel. So that is negative sine of the towel, right? So I need to write the towel down in here. The whole thing. Then what? Plus, minus, times, good. Times what? The derivative of what was inside. And that, what's in here, is not a chain anymore, right? It's no layers and onions. It's a quotient rule. So what I'm going to do next to this is I'm going to write down x squared plus 1, x cubed plus 4, prime. Just to let you know I still need to do some work, right? It's the derivative of the inside. And I think I'll do that derivative on the side, like scratch work. Do y'all see what I'm doing? So because that was last week and you're all experts at quotient rule now, we know it's the derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So derivative of the top times the bottom minus derivative of the bottom, 3x squared times top all over bottom squared. Clean it up, if you can, which here we can distribute. Let's see, I'm getting 2x to the fourth, but then over here I'm going to get a minus 3x to the fourth. Maybe I should write it down. 2x to the fourth plus 8x minus 3x to the fourth minus 3x squared. All over do y'all agree with that? And then combine some like terms together. We're getting like negative x to the fourth minus 3x squared plus 8x all over x cubed plus 4 squared. This right here is just this piece. And we're done at that point. So just take this and replace that whole piece with it. And that would be your answer. So you could say in this problem what we had was a chain rule, right? This was chain rule. And inside the chain rule we had a quotient rule. Is that fair to say? Yeah? Let's try a quotient rule that has a chain rule in it. This was a chain rule with a quotient in it, right? I'm going to give you a quotient rule with a chain rule in it. So how about this one? How about tangent of sine x over x to the fourth plus sine x. Oof, that's nice. I thought y'all were enjoying this, so I'm just bringing the pleasure. Look, this is very systematic, okay? It's very structured. You just have to identify what you're looking at and take your time. So what do you see? Quotient, right? That quotient is not sitting inside of something, right? The outer layer, if you want to think of layers, is really, the quotient is the last thing happening. Right? So ultimately, I have a quotient rule. So I'm going to start writing quotient rule down. Quotient rule says derivative of the top times the bottom, right? Well, this is the way I'm going to write derivative of the top. I'm going to write tan of sine x. That's the top, right? Derivative of that times the bottom minus the derivative of the bottom. I'm going to write like this times the top all over bottom squared. Do you all at least agree with what I've written down? I mean, that is the quotient rule on that? Yeah. I haven't actually taken any derivatives, though. So let's look at the pieces I have to take derivative of. Let's do this one. What is going on in here? Is that product rule? That's chain rule. It's tangent of sine, right? Tangent of sine of x. What's happening here on this one? It's just a sum product. You're just going to do derivative of each one separately, right? And that should be pretty clean. Derivative of x to the fourth, easy. Derivative of sine x, easy, right? So the only real issue here is that top left corner. And that's a composition. That's chain rule. And you just said that you were enjoying those, right? So what's the outer layer to this onion? Tangent. So you're going to take the derivative of tangent of this mouse. Secant squared of the mouse, right, which was sine x, times yes, cosine, because now you've done the outer layer, you've done tangent, you've got to go inside and take derivative of the next layer in, which was derivative of sine, which is cosine. You tack it on with multiplication. Once you get to the inside, the furthest inside layer, and you've done that, you're done. But I still have sitting next to that what? X to the fourth plus sine x. And I need that all in parentheses right here. X to the fourth plus sine x. Do I need this in parentheses? No, there's no addition or subtraction between those. So it's all one factor. You can just leave it. Minus, I'm right here. Derivative of this. 4x to the third. Plus cosine x, and then tan of sine x. All of this over the bottom squared. That stuff, I'm not going to write it down squared. We're done. Nah, we will just leave it. You get the idea, right? The method is the important thing here. I get a sense that you're enjoying this quite a bit.
So the bottom one, is that like the raw derivative, I guess?
The what?
The bottom one is the raw derivative?
Yes, this would be raw, yeah. But with this problem, I don't know what more you could do. I mean, you would have to distribute through to see if anything becomes like terms. I don't see anything that would be like terms. I would have zero hesitation with you handing me a function and taking derivative of it right now.
Even if it had like 5 different terms to it?
I wouldn't care. The thing is, that's what I was trying to tell you at the beginning of class. Once you have these rules, there's really no function that you can't break down. Now, it could be very ugly. Okay, it could be extremely ugly, but if you understand what you're doing, you should be able to do it. There's really no limits anymore, except if I threw in an exponential or a log, because we don't know what the derivative of e to the x is yet. We can guess what it is, but don't guess. Just wait till we get there, okay? All right, so let's talk about something else. We're